Hi everyone. So today I'm planning to discuss or solve a few problems related to continuity, subspace topology, and product topology. Basically, whatever we have, done in like past few lectures, or sort of, yeah, kind of mixture of all. So let us start with, a very basic and simple problem uh, for the moment. So let us define some function. Okay. So first, so let me see what's the problem. Yeah. Yes. So you have a function fx is equals to 1 upon x. So where it will be from? R minus 0 to where, guys? So know the graph of 1 upon x, right? It will be 2 into R, right? Can it take 0 at any point? No. So this is your map, right? Okay. What you have to show? To show f is continuous, and number two, you have to show f is open. So, you don't have to use here epsilon delta definition. Definitely, you can very well use that. But let's try to, you know, use the existing theory what we have developed for topological spaces. So let us see what is the graph of the function. I hope you guys know it. So yeah, these lines are not straight. Please manage with that. So this is what happens when it is between 0 to infinity, and otherwise it is like this, right? And so on. So if you remember, we have, okay, we haven't proved, but I have given you as an exercise. Even if you pull back or take the inverse image of basic open sets and check whether these are open or not, it is sufficient to see if something is continuous or not, right? So now let us, take, let us consider what are the basic open sets in R minus 0. You know that a real line R has its usual basis. What? See, whenever no topology is given, it means it's the usual or the induced from the Euclidean metric. So the basis for this is A comma B in R. This is basis. A basis actually, right? There can be many others that we have discussed in detail. Okay, so if I see just inverse image of these open sets, I'm done. But wait, your topology is from R minus 0. So what will be the basis for R minus 0? So for R minus 0, the basis would be just these open interval intersection with R minus 0. That's all right. Is that fine? Now, what you have to see, just the inverse image of these functions if you want to, oh sorry, these sets if you want to show it as an continuous function. So let us begin. So let A comma B be any open interval in R. Now AB is in say R. You have to look for this open set, right? So let us say U is equals to intersection say R minus 0. Now you see this A comma B can be here or like this, right? It can be any one of this form, right? So it means you have to make the cases. So what would be the case one, guys? So case one would be 0 belongs to U. So if 0 belongs to U, It means use of this form. A to 0 union 0 to B, right? Because it is intersection with, sorry, not 0 belong to U. It cannot be in U. 0 belongs to open interval AB. So U has to be of this form, right? Now let us see what is the inverse image. So what is the inverse image? The formula is, you have to see what is this. So let's say x belongs to this. This implies, or both ways implies, x belongs to A, comma 0 union 0, comma B. This both ways implies x belongs to A, comma 0 or x belongs to 0, comma B. Right? This both ways implies, what it implies? Something is wrong, right? F inverse, F inverse, F inverse. Sorry for these silly things. Basically, this is F inverse of A comma 0 union F inverse of 0 comma B, right? This is inverse image. So, it well behaves with union, intersection, complements. So, what this mean? F of x belongs to where? A comma 0 or F of x belongs to 0 comma B, right? And what is f of x, guys? This is just your 1 upon x. So it means 1 upon x belongs to a comma 0 or 1 upon x belongs to 0 comma b. So if this is the case, what can you say about x? So it's like this. So 1 upon x lie between a and strictly less than 0, or 1 upon x strictly lies between 0 and b. So what would happen with reciprocal? So when you take reciprocal, what happens? That's what you have to see. So it is like, or okay, yeah. So it's like, so this is the case, right? This is you have to carefully see. This is less than 0, right? So deal with this thing properly. So when you multiply, say, with x both side, the sign actually reverse, right? So if you do this x a, right, this will be what, or other way to do this is this. So you know that a is less than 1 upon x, less than 0. This implies minus a is bigger than minus 1 upon x. Now if you see, these are what, these are positive numbers. So whenever for positive numbers you have something is say x is 0, x is less than y, then what you can conclude? So what is the relation between 1 upon x and 1 upon y? The sign reverses, right? So this both ways implies what will happen, that x is bigger, minus x is bigger than minus x, right? Yeah, bigger than 1 upon a minus 1 upon a. Right, now you can, again do multiplication by signs. So this means 1 upon a is less than x. And x is less than 0 because 1 upon x is less than 0. So this is what you are getting. Okay, good. And similarly, this is one step, right? So this implies x is bigger than what? 1 upon b. I hope I haven't done any calculation mistake here. Pretty bad at sometimes doing I do calculation mistakes. So what we have done, we have just multiplied with minus, so the sign will reverse. Then what we are saying, take the reciprocal. So when we take the reciprocal, this should come here and this should go there. And when we again multiply with minus, yeah, something like that. So if there is a mistake, you can, figure it out. And b is bigger than 0, so this is bigger than 0, right? So what you are getting, if and only if x belongs to these intervals, 1 upon a, comma 0, or 1 upon b, comma infinity, right? So this implies x belongs to 1 upon a, 0, union, 1 upon b, infinity. Please check the calculation. I may do some silly mistake. Okay, it's good if there is a mistake. You should point it out. So what we are getting is, so this f inverse of u is nothing but 1 upon a, 0. If there's sign mistake, I'm again saying in this one, please check it. And these are open sets, right? So the union of any open set is open, any number of open sets. So this implies f inverse of u is open, where in R minus 0. Very nice, right? We haven't used epsilon delta. We just have proceed with the definition, what we have learned in topological space. Okay. So I will leave, the case 2 for you. That's pretty much simple. So if 0 does not belongs to a comma b. Simple as in, because now you have, you know, learned like how the thing is going on. Okay. So this is an exercise. Nice. Let us proceed with another problem. So, okay, this is actually nice problem. So let x be an uncountable cofinite cofinite space. What I mean by cofinite space is that X is equipped with cofinite topology, which includes empty set and all those sets whose complements are finite. And let f from x to r, real line r, be continuous. Show that. This is a very fun question. F is, yeah, I think it should be constant. Let us see what we can do. So, I mean, if you try to think in construct examples, you can definitely check, say, is fx equal to x? Is that continuous? Check it. Okay, because if it is continuous, according to this, it has to be constant. So, but in general, how to prove such things? We usually proceed by proof by contradiction. So, say, there you have 2 points, f of a, which is not equal to f of b. A comma b belongs to x. Okay, so what this happen? Sorry. What is the meaning of this? So see, in R, you can do one thing. You take, epsilon to be mod fa minus fb. say by 3, and if you take u equal to b ball, I mean, with the usual metric centered at a of epsilon and sorry, f of a and v to be ball centered at fb of radius, say again epsilon, the new intersection v is empty. Please show that. This just uses triangle inequality. Okay. So these are open sets, right? Where in R? So it means pullback of these. So this contains A, this contains B. These are open. Where? In X. Okay. And moreover, F this thing intersection with this is empty, right? You know F inverse is well behaved. I mean inverse image of a function under unions and intersections. If you don't know, then show this fact. In fact, for any family. Okay. So what this means, guys? X is equals to X minus, using De Morgan's law, union X minus F inverse of B. What is this? See, these are open in X. X is with cofinite topology. So this is finite. This is finite. Finite union of finite set is finite. So this implies X is finite. So you have a contradiction, right? So that's all. So, these things by definition, these kind of questions, these are like really, 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 really very important. So you should not uh, miss trying these problems. Okay, I have one more, but maybe that you guys can explore on your own, or maybe I can, give you little information about that. No, you will come across such questions. So, oh, by the way, in first question, I forgot to prove this is an open map. So this is your exercise. Okay. I mean, there are many problems. I'm just looking into book and yeah. Okay, one thing I like too much is this. Torus. So let us understand what is a torus. So the basic idea is you take a circle and you revolve it like this around some axis. Around some axis. So what you get is this kind of shape. Right? This is a hole. So it's like your cycle tube, just the outer thing. So that is what torus is. So what we will, so mathematically, it is like you can see this is just S1 cross S1, right? Cross product. You take a point in S1 and whole S1 you are getting for that point, then all points, this is like around this, you have a circle and around this you are moving, like this. So this will become a torus. Okay. But if you see, what is this? This has how many components? X naught, X1, X2, or say, yeah, X3, such that X naught square plus X1 square is equals to 1, and X2 square plus X3 square is equals to 1. You may think, or that's not wrong to think, that this is R4. But the kind of construction I have told you in green color, it looks to be in R3. It means this S1 cross S1 is in R3, meaning it should be homeomorphic to some subset of R3, like this green color thing we have done, right? So let me formalize this thing. So let's say, let me define it, then I can explain you better. X comma Y comma Z in R3. I'm giving you what will be exactly, this. I mean, this is just a way. So what we are doing is actually, we are taking a, circle where. So it's like this. Sort of you have something like this and you are revolving like, this around this axis. If you're not clear with it, do one exercise. Put Z, particular values of Z, wherever, from wherever to wherever it can be. You will realize that this will give you nothing but a torus. Okay. I'm not going into too details how this is happening. Okay. So the revolution is so this is a circle in X Z plane if you're so, and the revolution is also happening, you know, XZ plane, XY, X. So you can say that this is X. Okay, this circle is your circle which is perpendicular to say XY plane. Okay, and this circle, what it's a unit circle which is in XZ plane, and it's like center is like 200 something like that, and you are just revolving it around Z axis. It's like that. You can see, and this will give you that kind of tube, hollow tube. Okay, now the task is to show that this is homeomorphic to S1 cross S1. I want you guys to, do multiple exercises, and that will conclude this. So exercise 1. Show that any two circles in R2 are homeomorphic. Any two circle. I'm talking about circle, not disk. There is a difference. When you write in school area of circle, it's not a very correct word. It's area of the region bounded by circle. Okay. And exercise 2 is just I will give you the precise homeomorphism. And you have to check this is a homeomorphism. Okay. Let us take two circles. X, Y, 1, 2, x square plus y square is equals to 4. And maybe in XZ plane, since I'm revolving around it. Okay. So, this will be homeomorphic to S1. This will be also homeomorphic to unit circle S1 by above exercise. And we will show that this is, this torus. There is a homeomorphism. So this is a way to write. So H is a meaning homeomorphism from here to here. This is your homework. So what is H? Let me give you that map. Maybe you can, directly guess it. I may make a potential mistake. So, yeah, maybe there is a mistake. So please verify it, whatever you're doing. This also you have to show, huh? It's not very hard. Just see this component is fixed. Okay. I think this should work. If it doesn't, you know, you may see why not. Okay. Good. Yes, it will work. So you have to show that this map is also well defined. Meaning, does it actually go to the codomain, what I'm showing? Saying. So yeah, this is another task of yours. And let me discuss, another very important example. Maybe not now. Hmm, let me think, guys, huh? Okay, let me give an exercise. Show that f from r minus 0 to r, f of x is equals to sine is continuous. This also, I want you guys, to try using, definition of basic open sets and all, not just the continuity definition with respect to that, not just epsilon delta. You know very well how to do this with epsilon delta, and you have several results. Okay, let me see if I have some problem in my mind. I do have one. Yeah, these problems I usually like. So let us, whatever problem this is. So, let x be a straight line in R2. Any straight line. Okay. then you have to see that, yeah, what is the topology, I mean subspace on X when X is contained in, I think I have told you this, R with lower limit topology. Basically, this is lower limit topology, these kind of lower limits. So it should be like this. AB. These are the basic open sets. Yeah, we have discussed. As a subspace of the product topology. So, this question is of subspace topology also as well as product also. And Y, oh sorry, X number one as a subspace of say R with lower limit topology cross usual real line R. Okay. So you know the basis of lower limit topology. Let's write it BL. This is the basis. And what is the basis for the usual R? So I'm not writing anything here. So A comma B, right? So when you have finite, product. So the basis for this product space, let us call this say Y. Let us call this is it. Will be what? The product of individual, kind of elements among them. That will be the basis because we have shown that product topology is same as the box topology when your family is finite. Okay, so this will be something like this. A comma B cross C comma D. So these are your basic open sets. Now let us see. Let us take a line. So see, there are two possibilities when you take a line. Actually, there are many. So if the line is something like this, let us see what's happening. And let's say you take a point. Yeah, here, say, for example. Say this is some point, whatever. Now you know how the basic open set is there. So let's take something here, say A and B. Okay, so this is your A, right? And B is this. And let us take this cross product with some interval CD. That's what basic open set I'm looking in. The ambient space, meaning Y here. Then I will look for, the subspace, what's happening. Because, if you have the basis of the ambient space, what will be the basis of subspace? You just intersect with them, with Y. Sorry, with their subspace. So let's say you have some C here. And this is like some open D. So let us, properly try to plot this. So see what it would be this. This point will not be included, right? This will be here. This, okay, sorry. And this will not be included. And this region is not included, right? This all region is there. So when you zoom it or take the intersection of this, what kind of set you're getting? This point will be there and this will be open, right? Here, see, this is here, this is open. This is the precisely intersection. So what kind of, this thing is, if you just consider this as a real line, it is a real line, any straight line like this, right? So, just a second, guys. Yeah. So it is like if you have line like this. So what can you say about its slope? So its slope is less than 90 degree basically, and bigger than, 0. Tan of 90 degree will be the slope now. So yeah, so that kind of inclination. So in this case, these kind of actually interval we are getting, if you consider this, this is a line. You can show this is homeomorphic to R. So this is a line and these kind of open intervals you have. So when you take Y, it has what again? Lower limit topology. Because that's what the precisely, the open sets are. But we are not done. This is just one kind of line, right? Depending upon the slope, we will have another kind of lines, right? So let's say if you have something, so say, you are taking line X and X has slope tan theta. So theta here is lying between what? 0 and this is less than what? Pi by 2, right? Okay, very nice. I hope I haven't done any mistake here. Yes, this is fine. So now case 2 will be if you have some line like this. See, I mean, we can have several cases, but let's take this one first. Write the condition of on theta. I'm not writing. Okay. Now, again, you take some interval like this. So this will be closed. Something like this will be open. And say this will be closed. And something like this will be open. And when you actually take the, you know, intersection. So if you see like this open, right? And this is like, oh, sorry. Here it would be something like open. So this is the region what you are getting, right? Or can you take something like this? So this is open and like this. This thing me, this kind of picture allow me to think, oh, why can't I shift this, rectangle little bit up where these are meeting? So in this case, what is the intersection? So let me write it formally if you want. So for any a comma b in X. So let's say this is your a comma b, right? What you have this interval, say a to some a plus epsilon cross b to some, b plus epsilon, right? What is this? Intersection of this basic open set of the ambient space with X is nothing but just singleton a comma b. What it means? Every singleton is open. So in this case, X has discrete topology. So see, this is a very fun question. Lot of pictures and visualizations. Now, let me talk about the another cases. I will leave that as an exercise. So tell me what will happen in this case and tell me what will happen in this case. These are the only remaining cases. These are parallel lines, huh? So this is your X. So this is your X. So you can now quickly, evaluate and see what's gonna happen. So these are not difficult on the similar lines. So, you know, similarly you can do this. Where is the question, guys? I forgot, sorry. Yeah. So similarly,
You
you
can
can
take
take
this
this as an exercise.
second
Second
question.
question. Yeah. So yeah, I think that this is enough for today. I just wanted to discuss a few problems which I think are like very beautiful. So let's end this session with this, and in the next lecture, we will start with connected spaces. Thank you very much. I mean, there are many more problems which you can look from the books. Thank you.